And now for some robots. So, and I have to change my card. So, now for some robots. So, Hugo is actually software engineer by heart, I learned. So, but now today we want to talk about hardware stuff, so robots, and especially he wants to present us how this journey worked from becoming a pure software guy to hardware robots enthusiast, and we will show us some of his examples here on stage. So give him a huge applause.
Thank you, and good morning, everybody. Great to see that so many people managed to get up here a Sunday morning. So in the next 15 minutes, I will try to entertain you a little bit with the story of how I came to build this hexapod. Usually we have a regular introduction about who you are. I decided to reverse this for the sake of the story, because actually this is more about what I'm not. So I'm definitely not somebody with a math guru. I did my high school and polytechnic math with quite some trouble. Any teachers here? Well, let's forget about that. I'm not a design engineer. I don't make any of this stuff for a living. And I'm actually also not an electronics engineer, unless you consider blowing stuff up part of the engineering bit. I do have a little bit of a background in software engineering, so that was already helpful. And I have a 3D printer, and not that afraid to use it. So if you want to start something new, and in my case, I wanted to start with robotics because it looked interesting, it looked cool. Where do you start? So at first, everybody talks about Spot, nice quadruped robot, looks amazing. If you see the videos from Boston Dynamics, it's awesome. But it's actually kind of hard because you have to deal with balance and you have to deal with a lot of stuff. Two-legged robots, even more difficult. I can hardly keep myself on 2 legs, let alone a robot. So I needed something that was a little bit easier. And then I found a hexapod. And actually, if you start looking for hexapods on the internet, YouTube is full of videos of people building hexapods and doing stuff with them. So I decided, okay, that is maybe interesting to use as a getting started, as a hello world into robotics. So this talk is all about how I started with building this hexapod, how I took all the different steps to get eventually to a working system, and hopefully demonstrate it a bit without making the device fall off the stage. So how do you actually get started with building a hexapod? Well, actually, the first thing you have to do is quite a lot of math, because, yeah, it's angles, it's legs, it's movement. I'm not good at math, so I had to do quite a bit of research. I had to build some mechanics using, in my case, Fusion, to build up all the different components. And finally, electronics. Technically, you don't need electronics because you can get most of the stuff you need actually from AliExpress or wherever. But since we're building something from scratch anyway, why not build a dedicated piece of electronics as well? Let's go into the mathematics part. Actually, if you look at a hexapod, it's sort of built on insect leg. This is a typical insect leg. Has quite a few moving bits, but I'm actually interested in a few of them. The bits that actually make up a hexapod, in my case, are what we call the coxa. Hope I'm not offending any Latin speakers here. A femur and a tibia. And if you look at the typical motion, you actually want to be able to swing your arm back and front, and you want to twist it so you can actually move it. So that sort of looks like this. So if you look from the side view of a leg, I want to twist it here so I can lift it up. I want to twist it here so I can make some movement. And if you lift it from the top, if you look from the top, you want to lift it here because you want to move it forward. It actually resembles how your own arm moves in a lot of ways. Well, that was the easy part. So if you start looking into how to actually make a leg move, one of the first terms you meet is actually this, kinematics. For this presentation, 2 parts of kinematics are interesting, which is the forward kinematics. And the forward kinematics is actually saying if you know the angles of the joints we just described, you can probably calculate where they are in the world, where the tip is. Because actually the only interesting bit I need to know is where the foot of the robot will land or where it is at any given moment. If I know the angles, I can actually calculate that. Inverse kinematics is actually the reverse. We know we are at a certain point in the world, maybe because we've calculated that before or because we did some calculation and we decided this is where I want a particular piece of the robot to be. And then I have to calculate it back to angles that I can tell the joints to actually move. This is kind of hard. It depends a little bit on the mechanics. So again, hexapod really shines here because the mathematics is simple in the sense that there's a formula you can actually use to do this inverse kinematics. A lot of robot movement eventually, it's actually, well, it's a mathematical form of trial and error. You just do a bunch of calculations, you see which one fits best, and eventually you arrive at the point where you want to be. With the hexapod robot, because of the mechanical design and the limited number of angles it can actually do, you can actually make a discrete calculation. Well, get out your notebooks. This is it. I give you 3 minutes to copy it if you want. Actually, it looks very complex, and it is. I mean, I put in a lot of work in it. But if you look at it if you take a step back and you look at it, it's all angles and lines and straight angles. That's the stuff we actually learned in college. It's sinuses, it's cosinuses, and it's a little bit of measurements. And there's not too many of them. So you can actually, well, I don't know if you can remember, but I had to look it up again. But if we know this length of L1, L2, and L3, and we know the angle where it's at, which is actually the twist angle in this case, because we're looking at the top, we can calculate where we are. And we can calculate where we are with respect to the first joint, which is actually the twist joint. If we know that, we can start looking at the side view and decide, well, hey, if we know where we are, I can make a new triangle. And now the fun starts, because now I can start calculating this angle. I can start calculating this angle. Little bit of math later, you actually have the angles. So college math is enough to actually get you to a point where you do this. Most of the work was actually drawing this picture and then seeing, okay, I actually do remember little bits about my college math. This is all from the point of view of a single leg. This is how we do the kinematics and the inverse kinematics. If we want to move this in the entire world, stuff gets a little bit more complex. Because we've calculated angles, we've calculated the position using our kinematics. So we have some x, y, and z values. But what do they mean? The interesting bit about x, y, and z values is that they're with respect to a certain something. We define a place as 0, and from there we calculate what we actually have in terms of axes and distances. But yeah, with a robot, it's quite complex. It has multiple points, it has multiple origins. So we need to start thinking about frames. Reference frames, to be precise. Reference frames are basically points we define in space where we say this is a particular thing, and from this particular thing, we can start calculating distances and angles. So if you look at the hexapod, the first one that I've defined is the hexapod frame. The thing is at the position in the world. As most of you know, we have GPS, we have positioning, so we could actually decide this is where the robot is. And if they then move it a meter to the side, it moved 1 meter from this position to that position using a reference frame, which is our global GPS positioning. But now I want to move it in respect to its own body. For example, I want to move the legs 10 centimeters to the left of the body. Now I have to calculate the position of the body and make a new reference frame that actually tells me this is where the body is, regardless of where it is in the world. and then move it a little bit to the side. So that's the body frame we're using, which is funny for a hexapod because the body is actually floating in space. And then the last bit is or the second to last bit, is the coxa frame. Because we have this inverse kinematics we just talked about. We look at the legs from the side view because we're interested in the angles mainly. So we have to change the reference frame and say, if I want to do something to the leg, I need to do that from actually the joint that's twisting it. I can't do that from the center of the body. If I want to calculate where my arm is, I actually have to twist it like this. And I have to calculate it from this point. And then, of course, a very important reference frame is the tip. Where's the foot? If any of you worked with 3D mechanics or 3D modeling, you probably know a little bit of that. But actually, we can build translation matrices. This is something, well, easily found online, so I'm not going to go into that much depth. But actually, there's formulas, translation matrices that you can use to say, if I have a point in, for example, the world reference frame, I can apply a transformation matrix and translate that to a point in the body frame. And I can do the reverse as well. So that means that if I have a point in any of the reference frames we just discussed, any of the 4 reference frames, I can do a series of calculations to make that actually work into a reference frame for another part. So say I want to do a complete calculation, I want to do a complete movement, I decide where I want the thing to move, so I need to move the body and I need to move it in the world, for example, 10 centimeters to the side. I have to calculate the positions where all the legs end up, and then do a set of these translation matrices to actually get to that position. Talking about movement, it's not as simple as just moving the legs. I mean, I can move the legs, and the only thing that would actually happen is probably that the body moves a little bit to the side and starts leaning, because I haven't told it that it needs to have some kind of system to actually get from A to B. And knowing a hexapod, it stands on 6 legs. The body floats in space. So how do we actually move the body? Well, moving the body is the easy part. We can just tell it, move a little bit with respect to the world frame. But then we have to think about, how are the legs going to move? And that's actually the fun part of the hexapod robot. We have a thing called gate. And in this case, we have a tripod gate. And the tripod gate is a gate where we use all 6 legs in alternating sets of 3. If we know our math again, college math, if we have 3 points in space, we have a flat plane. We have something that's stable and equal. We can use the same technology for a hexapod robot. If we have 3 legs to stand on, we're actually stable. If they are on the proper sides, if they're equidistant from the body, you don't want to use the 3 legs on the left side or the 3 legs on the right side. But if you space them out correctly, you're actually always standing on a triangle. So what we can do is actually we can take 3 legs, keep them at a fixed position on the ground, move 3 other legs a little bit forward, put them to the ground, and repeat ad infinitum. That's our movement. That's called a gate. That's called a tripod gate. There's actually another gate that you can use with the hexapod robot, and that's the ripple gate. And that's a gate where you keep 5 legs on the ground, and you move only 1 leg forward a little bit. And the tripod gate is typically used if you want speed and a relatively flat or stable ground. A ripple gate is very good at navigating rubble or slow movements because it's much more stable because there's always 5 legs on the ground. Now, I mentioned that we have to move some legs forward. That's actually more difficult than you would think, because suddenly you have not only to think about the XY plane, how do we move 1 leg from position A to position B, but we actually have to think, how do we do that? Because if I just drag my leg forward, well, nothing will happen. Friction will actually stop the leg from moving, and the hexapod will start doing really strange things. So we have to lift it. So what you see here is a little bit of a calculation on how that actually works. So what I did is I split a movement of the leg in 3 phases. I made a lift phase where I said, okay, if you want to move from in this case, 0 to 0, and you want to move up. First you need to lift, then you move forward, and then you need to lower the leg. It's actually a relatively simple way of determining a lift, but what makes it difficult for hexapod robots is that the position where you are can change at any moment. We can't completely pre-calculate a trajectory and say, just follow this trajectory with a lift, because something might have changed in the meantime. We might have changed direction, we might have changed speed. So this calculation actually takes the entire motion we have for the hexapod robot, puts it in a certain time frame. For example, we have a 250 millisecond amount of time to move a leg. Then we calculate where the next position should be. And every time we make a step, we start from the position that we previously had. So if we are at this point, we know that we have completely lifted, so the only thing we have to do, we have to move forward. If we are here, we know that we are that close to the final destination that we need to start lowering the leg. And of course, you have to decide all the velocities. This is a little bit of the math behind the hexapod robot. Some key lessons that I've learned. Well, it's been a while, guys. It's really been a while. College was hard enough, and getting back into the habit of using sinus and cosinus is difficult, but actually quite doable. Another great tip is to use MATLAB for your calculations. Not everybody's. There's multiple tools that do something similar, but please make sure you do all your calculations properly. It's very hard to debug later on in the process. Keep track of your reference frames. You need to know not only what the point is you're working on, but you actually need to know in reference to what it actually is used. And very important, accuracy actually matters. I mean, the moment you start working in the real world, things start to go wrong, things start to go off. We're working with computers, so we're working with floats. Floats are, well, accurate enough. But suddenly, if you want to calculate stuff down to the millimeter and you take floats through an entire series of calculation, suddenly it might change a few millimeters. So instead of working on accurate numbers, you have to work on ranges and say, okay, this is probably good enough. Well, let's talk a little bit about the mechanics. First few things that we need to take away from the math part we already did. If you want to start working on the mechanics, there's a couple of important things you need to know. First of all is the length of the legs. So we did all our calculations, and all our calculations are based on those sinuses and cosinuses and the lengths of the angles. So you want to make sure that whatever math you already built or you worked on is capable of working with the lengths and the design you've made. And of course, you need to decide which joints you actually need to implement. Because, we just talked about a leg, but you have to work them into your mechanical design somehow. And a very important part is which servos you're going to use. Because, those joints actually need to be activated, they need to be motivated to move, so you need mechanics to move them. In my case, I use Robotics Dynamical servos. Very nice servos, very well suited to robots. They are controllable with an API, so instead of having to use some pulse mechanic, I can actually send a serial command to the robots. Downside of these is they're quite expensive. A tip up front, if you decide to build a hexapod and you use servos, calculate the entire price of all the legs, not just a single leg. That will save you some trouble later on in the process, especially if you have to explain it to the missus. Another interesting thing is the effect on timing. So I talked about the serial protocol. A lot of the servos use a pulse-based mechanism, so that's just a simple matter of activating it on a GPIO pin. These ones use a serial bus. If you have to send serial data to 18 servos, 3 joints per leg times 6 legs, 18 servos, it's actually going to take time, especially if your servos are at default 56,000 baud. That actually takes time. I never calculated that in my initial calculations, that I would need a certain window of time to actually start updating on my legs. It's not instant. But you can work around that. But we're here to talk about mechanics. Well, I used Fusion because, yeah, I'm familiar with Fusion, so let's start with that. First thing I did is actually create the most basic parameters that we just talked about. So here you can see the FX 100. That's actually a fixed setting. That's the femur length that we decided during the math part. Here we have the 100 or the 15 centimeters, which is the length of the femur that we've decided. So these are my basic references that I use to actually decide the size and shape of my robot. Next thing I did, I started putting in the servo motors because they're suited for robotics. So that also includes very nice detailed drawings about all the sizes and all the connection points, so I could make sketches of all the different connection points. So I made this and a little bit of design, like how would I think a leg would look like. The thing you should not ask me why I decided to start drawing at a 25-degree angle. That caused me so much grief, I don't even want to talk about it anymore. The curved design is also not what's eventually there, but the important part is we have a reference sketch that we can use to actually design our parts. Now, we have a single leg, but we actually have a bigger robot. So next thing was actually make a sketch on how I would actually fit all the robots in the entire body part. So here the connection points of the different coxhead joints are actually important parts. And the rest is filling in the servos, and then eventually deciding on a shape on how would I like to fill this up. Well, there's a couple of parts other that I needed. So I wanted a battery compartment in here because I need to store the battery somewhere. So I took some measurements and eventually came up with this piece of design. And it's connected, linked to the sketch that's actually doing the side view. So now I have two sketches that are linked together that will actually show me how the leg is structured from a side view and how it's structured from a top view. This will actually help you do the part design. Well, like I said, I'm not an industrial designer, but fiddling about with Fusion a little bit, you can come up with something quite decent. They have enough options to actually do stuff like rounding and bevel, so it was quite easy to actually translate the sketches you saw into parts. And the next step is actually try if you can print them on a 3D printer. That's a good step not to forget. Try if you can print them at all. Here I deviated from the curved design because I actually didn't like it, so I made a more straight design, which is actually defining the points where I want to go, dragging some lines in between, and making the parts work. Add some extra features, like I will talk about it in electronics, but I needed some mounting holes for the Raspberry Pi as well. And then you have to bring the entire thing together. So next to this design, I actually also have a design that actually gets all components together. That is very interesting because you can use it for a motion study. So here we have just the same parts without any changes, but now all connected together. And with tools like Fusion, with industrial design tools, you can actually take a tip, move it a little bit, and see, hey, where do I actually get friction? Is the movement I've decided possible? So this was also very important to see if what I wanted to do was actually possible. A very important thing that came out of this step in the design was actually how much freedom do my legs have? Because the calculations we did in the math part can move basically in any direction. But if you start doing the mechanics, suddenly the real world pops in. And yeah, we have limits. And the limits change. So if we twist this servo a little bit, it will actually hit the body a lot earlier. So you have to make some changes in your design to allow for a full range of motion. So if you look at the individual components, this is actually the beauty of what good design tools can do for you. They can make awesome movies. Thank you. So the parts here, this is actually a funny part. If you build something and you use some rigid material, it's nice to think about how you actually fit the parts together. So I had my first parts printed and then decided, well, actually I can't fit them together anymore because the servo, it fits exactly, but there's no way to actually slide it in without breaking pieces off. So redesign, add a little bit of a slide. You can see here that the dynamic servos actually have idlers connected to them, which is nice because they can feed the wires through. So made the holes a little bit bigger, fed the wires through, very neat cable management. So tips, make sure that you can actually build a device. Not only get a design that looks nice and works nice, but also get a design that's easy to assemble and easy to disassemble, because you will probably be doing a lot of that. Wiring is very important. Where are your wires? A lot of these design tools actually don't have easy ways to actually see, okay, how would my wires work around the system? So that's something you have to think of yourself. How do we deal with the wiring? And again, the angle. Let's forget about the angle. So, electronics. Let's build a dedicated PCB for controlling this thing. Why? Because we can. It's something I've never did before. I never built a single PCB in my life. I destroyed quite a few of them, but never built one. Some things I decided for myself I wanted to do. So first of all, I wanted to build it as a Raspberry Pi hat. So I can just stick it on top of a Raspberry Pi. So I can also use the Raspberry Pi and do some advanced calculations. So I'm probably going to be using some kind of MCU, microcontroller. But if you want to do any AI stuff or any vision stuff, you need a lot more horsepower. So if I can build a control PCB that will actually control the hexapod, and then have a Raspberry Pi that can communicate with it, suddenly I have a whole range of things I can start doing. And I can offload any calculations. So far that hasn't proved necessary, but well, we can. One of the first things you'll learn if you start getting into electronics is actually making designs. So I started with downloading KiCad, downloading the models for the STM chip. I did have a little bit of prior experience with the STM32F401 chip, so I knew what kind of peripherals it had. But in a short overview, 8 megabytes of flash. It has a floating point unit. Very interesting point to look at if you're doing these kind of calculations. And it had quite enough peripherals for my use. And the thing that made it really interesting for me is that it had an asynchronous single-wire UART, which is exactly the thing I needed to use for my Dynamixel servos without having to add additional components to get a single-wire serial port. And a lot of stuff. Most importantly, how to connect it to the Raspberry Pi. Raspberry Pi Foundation actually has very nice descriptions on how to do this. So this is 90% copy-paste. How does the pinout of the Raspberry Pi connector look like? What are the names of the different connections? And from there, it's a matter of wiring them to the right points of the GPU. This is actually the EEPROM, also as defined by Raspberry Pi, so they can detect what kind of board you're plugging into. So far, copy-paste. This got a little bit more interesting, because now suddenly we had to do something with power. Because of course, I don't want a tethered robot to a wire. I wanted to have it on a battery. So I'm connecting a LiPo battery that I had from one of my other drones. And suddenly I had 11.1 volts somewhere that I needed to use to feed several circuits. So I needed to feed the Dynamixel servos, which can run directly on anything between 9 and 14 volts. I had to power the Raspberry Pi, which actually needs to be able to draw up to 5 amps at 5 volt. I needed to power the electronics. And guess what? I cheated, because actually I'm not powering the electronics on the board. The Raspberry Pi is doing that. So I'm using the Raspberry Pi 3.3 volt source to actually boot my MCU. But I did need a 1.8 volt power rails to power some of the sensor components. Again, there's actually a lot of tools to help you do this. So for example, there's Texas Instruments. They have a workbench. If you plug in your values, like I need this amount of amperage, I need this amount of of voltage, it will calculate for you and tell you, okay, this is the kind of chips you need to use, these are the capacitors. So this is actually also copy-paste directly from TI Workbench. This is a copy-paste from a reference circuit that actually came with the chip I intended to use. And this is the thing I learned that I needed to add, so that's going to be in the next version. It's actually very nice if you can turn off the control board from the Raspberry Pi. At the moment, we can't. Talk about sensors. I wanted to have basically what I have in my drone, which is the most important motion sensors in there. So I want a magnetometer that can actually detect the magnetic north, so I can relate my motion and my navigation to where the actual north is. And of course, I need a gyroscope and an accelerometer just to be able to see if the motion that I programmed in is actually also the motion that is being seen by the system. Both of them are actually copies from the PX4 drones schematics, where they provided the schematics for how they connected their drones, and then connect them to the proper wires. The dynamixel connections, very important. It was actually quite hard to figure out what hardware components to find. Do you know how many GHT-type connectors there are in the world? Man. So, two-layer board. Why? Because it's actually the easiest and very beginner-friendly. SMD components. Well, I'm not into SMD soldering, so I decided early on in the process, if I'm going to build this board, I'm going to offload it. So I used PCB way to make most of the boards and add connectors. Actually, I still don't have enough connectors. And this is what it finally looks like. So we have the power connectors over here where we can connect the battery. We have the primary CPU over here. We have the connectors for the dynamixels. And actually, the most expensive part, the sensors, are also the smallest. I even have to look it up. Oh, it's supposed to be here's one sensor, and here's one sensor. And this one's really a millimeter by a millimeter. We're currently at revision 1.1. That should give you an indication how many revisions there are. If you ask what happened to the boards of the other revisions, the only tip I can give you is try not to apply 12 volts to MCUs. Another good tip, well, PCB design, it looks mystifying. I mean, the first time I looked at a schematic like this, I was like, no, I'm not ever going to be able to do this. This is too hard. No, forget it. Hire a professional. But actually, it's doable. It's a creative part. It's mostly like drawing. You put all the components there, you drag them in the right spaces, and actually dragging the traces at some point is more about aesthetics than actually making it work. And again, I try to avoid all the hard stuff. There's stuff like differential pairs that you need to worry about if you have USB. There's, if you really go high frequency, you have to deal with radio, EMI. Let's forget about all of that stuff. This is a low-speed, digital signal-only board, so relatively easy to do for a beginner, and enough tutorials on YouTube to actually help you get it done. One interesting tip I can give you is try to add a debug board if you do that. The first two versions of the board didn't have a debug port. The first version was because I completely forgot it. The second one was because I uploaded the wrong design to PCBWay. Now I'm up to the third iteration, and hopefully now I will actually remember to put on the debug port. Oh, and another important part is, yeah, add something so you can reboot the board remotely. Now I have to unplug the cables every time I need to reboot it. So, what's next? We have math, we have a design, we have a 3D printer, so we actually have some physical components, we have some electronics, thank you PCBWay, and now we have to do some firmware design. Firmware design, again, I have a bit of background in embedded software engineering, so some of this stuff is actually relatively well known to me, but if you look at the bare basics, it's not that hard. So you need a control loop. That's the easiest way of doing it. There's many other ways, but I went for the easy way, which was a control loop. I need to decide where are my servos at the moment, because you always want to know where you are the moment you start with something. I want to update some key values, so maybe I changed velocity, or I changed heading, or I changed anything in the system. Then I need to run the state machine, and the state machine is telling me, are we standing, are we walking, are we in power down? Whatever we are doing, we need a state machine to decide what is the next step, what should the next step be. And then depending on the state, we can actually do the calculations involved, like doing the kinematics calculations, and decide where our legs should be. Which legs should be on the ground, which legs should be moving to the next position. And some safety constraints. If you start working with physical devices, it's very nice that if you have a calculation that well, even if you trust it completely, stuff always goes wrong. So add a safety that basically says, well, I could technically send this angle to your servos, but your servo won't be happy. So I will just prevent you from doing that. Saves a lot of servos and saves quite some PLA. And once everything is done, you write the new positions back to the servos, and you expect the device to move. This is the entire control loop for making this. I'm skipping some of the parts, like how do we actually do the calculations, and getting from the inverse kinematics all the way to doing the calculations is quite some work, but here you are. So some of the key components I used in the firmware, of course, the STM32 SDK. It takes a lot of work out of your hands to use that. So you can give it a chip configuration, and it will basically get you a mostly working project that you can already upload to your STM32, and it starts doing stuff. So it's filling in the blanks. The blanks might be difficult, but it's filling in the blanks. Another interesting project is CMSS DSP, which is actually a digital signal processing library, but has a lot of math components. And one of the great things they have, if they have highly optimized versions of all the sins and cosines and tangences, everything you need, they have highly optimized versions specifically for the STM32 ecosystem. So it makes it a lot faster. I built my own library, hexapod math, with all the calculations. And I have, of course, a Dynamixel library to actually control the servos. Well, I talked a little about the state machine, but it's very important to constantly know, okay, why am I doing this next step? What changed in my inputs? What changed in my system? And so, for example, I mentioned the safeties. If one of the safeties triggers in the software, it actually updates the state machine and says, okay, the next step you should is just go in power down, so it will prevent itself from hurting itself or doing more difficult calculations. Now, we have the firmware, quite a bit of hackery, and then actually comes the interesting bit, how are we going to try it? So you can build the entire robot and build it, but actually I found a project called Gazebo. And Gazebo is actually, it's a robotic simulator. It's a university project, it's actually quite active, used a lot, and it has a complete physics simulation model. Way better than what you expect, well, than the physics you get out of a game engine. This is really a physics engine that's suitable for trialing robotics. So I started building my entire robot in this system. So I had to decide, okay, all the lengths and all the measurements I had, program them in, add the joints, which are all the angles, and then you can start seeing the robot move, and you can start taking measurements. Physics is actually kind of interesting, because suddenly you have to do with stuff you never actually used, like, or in my case, inertia, weight, servo power. So it was actually quite interesting to learn about these concepts, because the first time I built this robot, and I used all the models that I got from Fusion, imported them, and it worked. And I said, okay, go move, and it suddenly launched itself into space. After getting the robot back from the moon, I looked at what's happening, and actually I completely forgot to put in any weights. So all the components were like 1 grams. Yeah, if I apply, and the servos were at max, so I applied a humongous amount of servo power to lift up a leg to a 1 gram thingy. Well, you can think about what happens. It gets launched to the moon. So I had to go back and say, okay, how does this work? Again, I'm not good at this stuff, so back to Fusion and see if we can actually make it work. Well, let's see if we can get this to work. So this is Fusion. You will see that it will add a hexapod at any second, the hex spider, and it will actually go to the motion. Now, this is the standing motion, and here you can actually see the motion of the hexapod moving. And if you look carefully, you can see the tripod movement by moving 3 legs alternating on the screen. And this is actually happening real time. The software that's used to actually make this model move is the same software I'm using to actually make the real world model move. So I can trial and I can test any movements I have, I can test here before I actually upload them to the servo. Saves a lot in development time and debugging time. So get it actually on the chip. Oh. I placed that, not very handy for you guys, I guess. But first thing with the STM, make sure that your pin-out design matches your physical design. Generate the code so you get all the bits and pieces that you actually do. And the rest is applying coffee. Lots and lots of coffee. I think I worked on this for about 6 to 7 months just to get everything going. Of course, not full time. There's other stuff I have to do. But yeah, it was kind of hard to do. Even once you know all the steps, it was building up and redoing stuff and getting back to previous parts and saying, hey, why doesn't it work? The main lesson that I learned here is actually to build up your software piece by piece. So having a simulator made it so much easier to actually start building up the robot, because I could actually verify and test source code with just a single click instead of having to go through the robot, upload it, see if it moved, wondering whether or not it was electronics, a connection, a wire, or the software. Some interesting bits. Of course, you start being very careful, so you move very slow. And I actually moved so slow that the servo updates were under their movement threshold. So they actually had to move a few ticks for me to register the movement with the API, and I moved so slow that I didn't register. So I was very surprised when the device didn't move. But going faster in this case helped. Make a mix of the expected values. The real world is nasty and full of surprises. So I started out with using completely the actual values reported by the servos. Eventually, I made a mix and saying, okay, I take the value that I think it should be. I take a little bit of the value that I actually measured, and I use that as the basis for the next calculation. Makes it a lot more stable. And of course, just repeat, add safety code. Don't blow up your servos, don't destroy your model by not adding safety mode. There's actually some interesting calculations in the inverse kinematics, that if you go over a certain angle with your design, it suddenly flips the femur angle. Because actually, if you want to go from this point to this point, and you have a triangle, you can go both ways. You can go this way, or you can go this way. And at some point, the calculation decided that this way was more optimal. But now my servos are set like this, and the next step is suddenly here. That makes some interesting motion. If you want to go ahead and do this, well, there's a couple of references you can use. Of course, you can use this presentation, and I really hope it was inspiring in helping and giving some pointers on how you could approach this. But one of the things that really helped me a lot was this book, Modern Robotics, Mechanics, Planning and Control, which is actually a book about everything you wanted to learn about robotics, but never could. So if you want to get into this field, this is really a great thing to use. Another great resource, Phil's Lab channel. if you're not into electronics, he has some awesome videos to get started. And he actually has a course on VettaFel that you can follow for basic signal design, which is enough electronics background to build your own PCB to make one of these robots work. And with that, I would like to thank you for listening to me for close to 50 minutes. I think we have a few minutes left for questions.
Yes, right. So first, thank you. And for everyone in the back rows, so here it stands, right? You can see it.
Yeah.
Maybe you can come back later in front. But first of all, we have time for questions, and we have a mic here, and we have a mic over there. Can you go to the mic there?
Really cool.
Yeah. Yeah. Okay. No.
Yeah, it's working. How you did the references to the real world? Because all the measurements are relative, right? So it's like servos showing relative angles, accelerometer showing inertia you got, like, but how you get, okay, I'm moved 1 meter and not like 50 centimeters, for example.
Yeah. So it's a good question. Like, how do you actually move for longer distances? It's about sequencing the gates. So if you look at the tripod gate, I move 3 legs forward, I put it to the ground, and I alternate a movement. So the actual legs move in a sequence. And the way I can measure the distance measured, and I can keep track of that, is I set a velocity. And once I've set a velocity, I make time slices and say, okay, I do 5 updates a second. So I know that in 5 seconds, I will have moved this amount of distance. Or actually, I know per increment how much movement I have generated. So the body reference frame is used to keep track of the movement in the world. So I can say, okay, I have moved 5 time slices at a velocity of 15 millimeters a second. So I should have moved X. And then I can keep on calculating that. And the legs actually move with respect to the body frame. So it's only the world frame that keeps track of the velocity. And I calculate everything back, saying if I'm moving at this velocity, this is where my front leg should be at a given moment in time. Does that answer your question?
Yeah. Okay. Any more questions? Yeah, everyone is pointing to the robot here in front. But you're also answering questions in area 42. So just come around.
If people are interested or actually want to see it work, I'm at area 42. I'm happy to demo it a little bit. So come and have a look if you want to.
Why don't you show for us how it moves?
Yes, sure.
Okay, so
this is a stand-up motion. I'll lift it up for the camera in a sec. But this is a stand-up phase, and now it moves to the moving phase. So this, and you actually see that it's a little bit jittery, and that's because I didn't program any velocity. So I do 5 updates a second, but the servos are way faster. So they do their update in the first bar of their second. And I should actually calculate the velocity better and say, move at this distance with this velocity, so the movement is a lot smoother.
So the question was, how fast can it go?
I haven't tried yet. I built in some limits, again, reminder of the safety thingy I mentioned. But at the moment, I programmed it at this limit, and this is, I think, 25 to 30% of what the servos can do. So I should be able to make this move a lot faster.
Can you make it third?
No. That's actually quite difficult. So that's the next project. Maybe next year. Yep. It's all on my GitHub. GitHub Spark 404. All the code is there, all the designs for the electronics, everything is in there. And if you're missing something, send me an email and I will come and help you get it.
Okay, so thanks again, Hugo, for